Okay, we'll start today. Good afternoon. So we'll start the ion exchange chromatography. Already we have discussed the liquid chromatography, column chromatography, HPLC, high pressure liquid chromatography. So among the various separation techniques, the ion exchange is the most popular name because of its used for water softening. It is also unique in terms of its versatility and historical developments. Besides the well known use of ion exchanges in water treatment, they find use in industry, nuclear fuel processing, hydrometallurgy, agriculture, and biology. So, before discussing the subject in detail, let us have a look on the objective or what are the points we will cover. The basic features of ion exchange mechanism, then classification of ion exchangers, synthesis of ion exchange resins, what are cationic, anionic, and amphoteric exchangers, and trade name of some ion exchange resins or ion exchange with their nomenclature, then resin properties like moisture content, particle size, cross-linking capacity, distribution ratio, equivalency of exchange, all these things. Then the operating methods, both batch operation and column operation, and also to give an idea about the moving bed operation. Then ion exchange in mixed aqueous organic media, then specific cation exchangers, synthetic inorganic ion exchangers, then applications. So basic features of ion exchange mechanism. The term ion exchange generally means the exchange of ions of like sign between a solution and a solid highly insoluble in it. That means when ion exchange will take place, a substance will be formed by exchange of ions which is insoluble and it will give the precipitate. Simple reaction if you see when you are adding silver nitrate to sodium chloride solution, so there will be exchange of ion. Nitrate ion of silver, it will be exchanged by chloride ion, so silver chloride will be precipitate. It's a simple criteria. But in case of our M, what we are using for this ion exchange chromatography, here we have to separate the substances. So the same principle also plays role here, but in this case we should take a reversible process so that the ion exchanger that can be regenerated after separation, it can be regenerated. So that's why this is the uh, difference between what simple exchange of cation and anion and in case of ion exchange mechanism. So the solid known as ion exchanger carries exchangeable cations and anions. When the exchanger is in contact with an electrolyte, these ions can be exchanged for a stoichiometrically equivalent amount of other ions of same sign. Carriers of exchangeable cations are known as cation exchangers, and carriers of exchangeable anions are known as anion exchangers. And certain materials are there, they are capable of both exchanging cation and anion, so they are known as amphoteric exchangers. So typical cation exchanger you can see here, your calcium chloride which is soluble in water, and NaX. Here is X. X represents the exchangeable anion here. So chlorine will be replaced by X, so that calcium, that X2, it will form the compound which will give the precipitate. Sodium chloride will be in aqueous, and CaX2, it will remain, it will give the precipitate, or it will absorb to the exchanger. So similarly, the anion exchange reaction, HCl we have taken, and sodium sulfate for example, which is soluble in water. So X, this sodium will be replaced by X. So and X2SO4, which may be insoluble or it will adsorb on the exchanger surface. So the X represents the structural unit of the ion exchanger. Okay. In the first process, a solution containing dissolved calcium chloride, say something like hard water. In hard water is due to hardness of water is due to the presence of salts of calcium and magnesium. So in case of hard water, let calcium chloride is present. So when it is treated with a solid exchanger like NaX containing exchangeable Na plus ion, the exchanger removes the Ca2 plus ion from the solution and replaces them with Na. So thus the cation exchanger in Na plus form is converted to Ca2 plus form. Okay. So the ion exchange, with very few exceptions, is a reversible process. In water softening, a cation exchanger has lost its Na plus ion and can be regenerated with a solution of a sodium salt such as sodium chloride. Ion exchange resembles adsorption in that in both cases a dissolved species is taken up by a solid. The characteristic difference between the two is that the ion exchange, in contrast to sorption, is a stoichiometric process. Every ion removed from the solution is replaced by an equivalent amount of another anionic species of the same sign. However, in case of sorption, a solute, an electrolyte or non-electrolyte may be taken up without any species being replaced. Okay, therefore, so from the above discussion, it emerges out that a useful ion exchanger must have the following requisites. It should have negligible solubility in the medium to be used. It must contain sufficient number of accessible ion exchange groups, and it must be chemically stable. It should be sufficiently hydrophilic to permit diffusion of ions through the structure, and is at a finite and usable rate. The Schwellen exchanger must be denser than water. Then classification of ion exchangers. So different synthetic and natural products, they show ion exchange properties. These exchangers can be either cation or anion exchangers. So a simple broad classification can be natural or synthetic depending upon the origin, and again they can be again categorized as organic or inorganic. For the purpose of simple presentation, we will select the first classification, that is natural and synthetic. So what is natural ion exchanger, examples, and synthetic ion exchangers. So in natural ion exchangers, they must be crystalline, and they include the crystalline aluminosilicates with cation exchange properties. The typical representative of this group of materials are zeolites, and the minerals like analcite, that is containing silicon, aluminum along with sodium, chabazite, and naturalite. All these minerals have a relatively open three-dimensional framework with channels and interconnecting cavities in the aluminosilicate lattice. So, if you know the structure of silicate or silica, SiO2, so it is having tetrahedral structure, and silicon is connected to other silicon through oxygen linkage. So there is a cavity as the tetrahedral structure, it will have some vacant space. And the silicates, and these are the phyllosilicates or aluminosilicates, they are having structure similar to silica, in which aluminum and silicon sodium, they are inside the case and still some vacant space are there. So the zeolite lattice consisting of SiO4 and aluminum O4 tetrahedra as mentioned here. These have their oxygen atoms in common. Because aluminum is trivalent, the lattice carries a negative charge. The charge is balanced by alkali and alkaline earth cations, which do not occupy fixed positions, and they are free to move in the lattice framework. These ions behave as counter ion and can exchange with other counter ions. Okay. There are other aluminosilicates which lose layer structure having cation exchange properties. These materials carry their counter ions in between the layers of the lattice. Typical mineral of this type is montmorillonite with the approximate composition Al2Si4O10OH2 NH2O. Such minerals swell in one direction, increasing the interlayer distance. So when distance will increase, they will exchange the cation. It may be important to mention here that certain aluminosilicates can also have as ion exchanges, also behave as ion exchanges in montmorillonite, kaolinite, and feldspar of sodalite and camerinite group. The exchange of OH minus for Cl minus, SO4 sulfate and phosphate, that means hydroxyl ion, can be extended for chloride, sulfate and phosphate has been observed. There are some problems with the use of zeolite as ion exchangers because of some of their properties. Like zeolites are soft minerals and thus are not very abrasive resistance. They have poor mechanical strength. Their framework are more rigid, hence less open. They swell very little, and the counter ion in their pores do not move very freely. Above all, they suffer partial decomposition by acids and alkalis. So this is a problem with zeolite. And another lesser known variety of natural ion exchanger is some type of coals. They contain carboxylic and possibly other weak acid groups. They thus can be used as cation exchangers. Most of these materials swell excessively and are decomposed by alkali. They are therefore stabilized before use. Soft and hard coals are stabilized by metal ion solutions. Most lignites and bituminous coals and anthracites can be converted into strong cation exchanges by sulfonation with fuming strong sulfuric acid or fuming sulfuric acid. These coals have very limited applications. Then we'll move the synthetic ion exchangers, which is vast or nowadays it is readily used. Virtually, the field of ion exchange has been dominated by organic ion exchange resins. An almost unlimited variety of resins with different compositions and degree of cross-linking can be prepared. That means if the resin cross-linking will be there, then it will increase the cavity or pore structure will be generated there. So whatever synthetic ion exchanges we are using, most of them are cross-linking polymers. The resins consist of an elastic three-dimensional network of hydrocarbons which carry fixed ionic groups. The charge of the group is balanced by mobile counter ions. As a matter of fact, these resins are cross-linked. These resins are cross-linked polyelectrolytes. In cation exchanger, the matrix carries ionic groups like sulfide, carboxylate, and phosphide, and in an anion exchanger, it carries groups such as ammonium, NH3 plus, NH2, that is secondary amine, ammonium, and also tertiary ammonium. An ion exchange resin is one single macromolecule. A particle is one single macromolecule. The chemical, thermal, and mechanical stability and the ion exchange behavior of the resin depend chiefly on the structure and degree of cross-linking of the matrix and on the nature and number of fixed ionic groups. So, as pointed out earlier, that ion exchange behavior of the resin is mainly determined by the fixed anionic group. So, the number of groups which determines the ion exchange capacity. The chemical nature of group to a greater extent affect the ion exchange equilibrium. So, you can see for example, the groups like carboxylate, they are ionized only at a pH at a high pH, and at low pH they combine with H plus, forming undissociated carboxylic acid. Thus, they no longer act as fixed charges. On the other hand, strong acidic groups like sulfide, they remain ionized even at low pH. Similarly, weak base groups like NH3 plus lose a proton, forming an uncharged NH2 or amine group. When pH is high, and strong base groups such as trimethylammonium, it remain ionized even at high pH. Thus, the operative capacity of weak acid and weak base exchange is more pH dependent. So, in the liquid ion exchanges, the high molecular weight amines and quaternary ammonium salts, they behave as liquid anion exchanges. They extract the anions and anionic metal complexes. With a similar analogy, some authors may classify alkyl phosphoric acids, sulfonic acids, and carboxylic acids as liquid cation exchanges. Okay, then the synthesis of ion exchange resins. So different chemical routes are followed to prepare the ion exchange resins. So it may be difficult. Hence, to highlight the synthetic chemistry of ion exchange resins, some discussion will be only taken. Detailed synthesis we cannot do here, or we cannot discuss here. So what are the different cation exchangers and simple how they can be synthesized, that process will think here. So what are the three-dimensional cross-linked matrix of hydrocarbon or resin can be obtained. So this can be achieved in the following way. Monomeric organic electrolytes can be polymerized in such way that a cross-linked network is formed. The matrix can be built from, just 1 minute. Oh, sorry. Please, just 1 minute. Okay, sorry. So, how they can be achieved? Monomer, the organic electrolytes that can be polymerized to give cross-link polymers. The matrix can be built from non-ionic monomers, and the fixed ionic groups are then introduced into the completed network. That means first the monomer first we have to polymerize, and polymerize will have the cross-linking structure with the cation exchange groups, or the matrix, that means the polymer can be built from non-ionic monomers. Then we have to, the ionic groups will be fixed or they can be introduced in the complete network. Then the fixed ionic groups are introduced while the polymerization is still in process. That means initially the monomer will contain the exchangeable groups that can be polymerized to give the polymer. That is one process. Second one, we have to synthesize the polymer, then we have to fix the exchangeable groups. Third one, during polymerization, the monomer may not contain the exchangeable groups, but during polymerization, we have to introduce the groups, ionic groups. Okay, so these three are the processes. So while synthesizing resinous exchanger, it should be kept in mind that it should be sufficiently cross-linked to have negligible solubility. So if it is a cross-linked polymer, generally normal polymers may be soluble in some solvents, but cross-linked polymers are mostly insoluble. The cross-linking should be such that it should be able to swell only. The polymers which are too high cross-linked cannot swell. The mobility of counter ion in such resins is so slow that ion exchange is difficult to take place. So the method of synthesis should be such that the degree of cross-linking can be controlled. Most of the ion exchange resins are made by either condensation polymerization or addition polymerization. Okay, so first the cation exchangers with different processes we'll see, by condensation, addition, polymerization process. Then we'll go to the anion exchangers and amphoteric exchangers, how they are prepared. So the cation exchangers, a broad variety of cation exchangers with fixed ionic groups of different character and different acid strength are commercially available. The most common of these are strong acids resins like SO3 minus, and weak acid resins with carboxylic acid groups as COO minus. Even if we consider these two types of resins, the resins of various strength can be made, since dissociation constants are affected by nature and configuration of units to which the groups are attached. So many ion exchangers contain two or more different types of ionic groups, and they are known as bifunctional or polyfunctional. Now, by condensation polymerization, we can prepare these cation exchangers from phenol. So when phenol reacts with sulfuric acid, we will get the phenol sulfonic acid, and when it reacts with formaldehyde, this is CH2CHO. So we'll get the this phenol formaldehyde resin having sulfonic acid as the exchangeable. Okay, so monovalent or polyvalent phenols like resorcinol and naphthol instead of phenol, and other aldehydes instead of formaldehyde can also be used. Phenolic groups can act as a fixed ionic group, but the resins have a very low acid strength. Groups with higher acid strength can be introduced by various methods. So the easiest course is the sulfonation of phenol prior to polymerization. So we'll get phenol sulfonic acid, then we have to polymerize. Yeah, condensation polymer. Then by addition polymers. The area of synthesis of ion exchange resins is now dominated by addition copolymers prepared from vinyl monomers. They are more chemically and thermally stable than condensation polymers. Okay, styrene and here divinyl benzene we have taken. So then we'll go for addition polymerization. Moreover, in addition polymerization, the degree of cross-linking and particle size are easy to control. A well-known cation exchange resin is obtained by the copolymerization of styrene and a small proportion of divinyl benzene followed by sulfonation by treatment with concentrated sulfuric acid or chlorosulfonic acid. So this one polymer is formed with styrene and divinyl benzene addition polymerization mechanism I will not discuss or we may not discuss here. So when this polymer will be formed, then what we have to treat with sulfuric acid so that the sulfonyl group will be attached to the para position. This is one polymer chain, this is one polymer chain, this is cross-linking one having side chain and some valencies they are satisfied with sulfonic acid group. So the role of vinyl benzene is act as a cross-linking agent because here it is you can see the two double bonds are there. So functionality is 4. One double bond functionality of the monomer is 2. So this carbon and this carbon the chain growth will be there. So two double bond means functionality is 4. So one can be used for cross-linking or when the functionality of the monomer will be more than 2 that is 3 or 4 then you will get a cross-linking polymer when it will be polymerized. So therefore, the role of divinyl benzene is as a cross-linking agent. Pure divinyl benzene is not easily available. The commercial product consists of different divinyl benzene isomers around 40-50% and ethylene styrene around 50%. Therefore, ethylene styrene is also introduced in the matrix. The degree of cross-linking can be adjusted by varying the divinyl benzene content. So if one monomer amount will control, then degree of cross-linking will also be controlled. So about the anion exchanger, the earliest anion exchangers synthesized weak base amino groups like NH3 plus and NH2 plus also having the not double bond, two linking groups will be here. So this is the structure NH3 plus and this is trimethyl ammonium. It is simple ammonium. NH3 plus means one bond it is linked to the resin or the main chain. So this is three valencies of nitrogen is 3 but as 4 groups are attached so it is NH3. This is hydrogen these 3 and one is for the main chain. So it is ammonium or here NH2 plus 2 side chains will be there. So these are the weak base amino groups. Subsequently, resins with strong base quaternary amino groups were prepared. It was followed by synthesis of resins with strong base quaternary phosphonium groups and tertiary sulfonium groups also. Phosphonium and sulfonium groups can also be used. Like cation exchanges, they can be also prepared by condensation and addition polymerization. So by condensation polymers, which is formed from metaphenyl metaphenylene diamine by and condensation with formaldehyde. Metaphenylene diamine condensation with formaldehyde. So NH2 CH2 again another compound. So there will be cross linking here because this main chain will proceed here. Here the side chain again there will be cross linking. So the aldehyde reacts with the amino group in the presence of in this process the secondary and tertiary amino groups are formed. Thus, the resin are polyfunctional. Aliphatic polyamines, which are not as weak basic, can also be condensed with aldehyde. Then with addition polymers like cation exchangers, a commonly used anion exchanger resin is prepared by copolymerization of styrene and divinyl benzene followed by chloromethylation. That means introduction of CH2Cl group, say in the para position, and interaction with a base such as trimethylamine. The polymers containing quaternary ammonium group are strong bases, and those with amino or substituted amino groups show weakly basic properties. So CH2NCH3 plus, this one, and Cl minus will be formed, the anion exchanger. Then the amphoteric exchangers. The anion exchangers which contain both acidic and basic groups are known as amphoteric exchangers. Number of exchangers of this type has been synthesized, but only we will discuss here. Just let me check whether net is there or not. Yes, it's working. Yesterday it was not working, that's why. Okay. So well-known resin contains both strong base and acid groups is prepared by copolymerization of styrene, vinyl chloride, and a cross-linking agent, vinyl chloride and a cross-linking agent followed by quaternization with and sulfonation of the product. So vinyl chloride and divinyl benzene we have given here, DBV. So vinyl chloride plus, so it will give the polymer, and when treated with tertiary amine, trimethylamine, so that chlorine will be substituted by this one, so you'll get an anion exchanger, and when again with sulfonation, so the benzene ring will be sulfonated, so it will act as cationic exchanger, this is anionic exchanger, so both it will act as the amphoteric exchanger. So among the amphoteric resins, the most important are one known as snake case polyelectrolytes. They are conventional cation or anion exchangers with which polycation or polyanions respectively have been formed by polymerization. A typical example is that a snake case polyelectrolyte can be prepared by converting a strong base anion exchanger to acrylate form, and then acrylate anion is polymerized in the resin. The linear chains of the polycounter ion are so in- intricately intrude with the cross-linked matrix that they cannot be displaced by other counter ions. The situation is something like a snake trapped in a cage. So then we move to the trade names and some nomenclature. We have seen some commercially available ion exchange resins, the manufacturer and their trade name. So trade name like Doex, Amberlite, Geocarb, Duolite, Leolite. So these are the trade name. The nomenclature. The trade name of resins are generally so named that the basic structure is readily apparent. For example, if you take the name Doex resin, it will include type Doex 50, Doex 50W. That means the cation exchanger Doex 1, 2, 4, 21K, it is anion exchanger. So this X, the number, or the divinyl benzene group, how many? Like X8. That means 8 divinyl benzene groups will be there. Mesh size also it is mentioned there, 20 to 50, that based on the US standard. And ionic form which is there, so sodium. For example, the label will carry something like this, type 50, that means DOX50. X8 divinyl benzene repetitive units will be 8 units will be there, Mesh size, that is the size of the particle 20 to 50, ionic form, so that is it is cationic or anionic you have to mention here. So sodium is means there cationic form. So the resin properties. So before putting in the particular application, some of the important properties of resins are the moisture content, particle size, cross linkage, capacity, distribution coefficient, equivalency of exchange, resin selectivity. Okay, so the first one, the moisture content. The moisture content of the resins is determined in the usual manner by heating it at 110 to 115 overnight to a constant weight. So, however, several precautionary steps are necessary in this exercise. For example, some resins are thermally unstable in the hydrogen and hydroxyl form, and therefore they should be converted to a stable form before oven drying. So samples which decompose at this temperature are occasionally dried at room temperature or over phosphorus pentoxide for longer period of time. Then the particle size, the most important one. So the importance of particle size for proper column performance in an ion exchange unit is quite obvious. So rate of exchange, pressure drop, and backwash expansion are all dependent on particle size. So the particle size for most of the ion exchange operations, the effective size is zero point 0.4 to zero point 0.6 millimeter diameter is preferred. This corresponds to particle size distribution falling between 20 and 40 mesh screens. The ion exchange reactions are mostly conducted in the aqueous media in which the particle have fully hydrated diameter. So this is the value that is to be taken into consideration. The size of the water soluble resin will depend on the type of functional groups and the amount of cross-linking of the polymer. So the size of the particle is one of the parameters affecting the rate of ion exchange reaction. Besides this, the other parameters affecting the rate are size and charge of the ion involved, degree of cross-linking, and temperature. So these are the factors which is responsible for particle size. So generally, the smaller particles like 50 mesh are physically more stable. This is important when resin is mechanically moved or it goes through large volume changes. In the cross-linking, when we will give the second variation, because after polymerization, the variation is the cross-linking, so which it can be introduced into the copolymer bed, is that the cross-linkage. As mentioned earlier, the cross-linkage in a styrene divinyl benzene polymer refers to the fraction of divinyl benzene content. Thus, a resin of 8% cross-linkage is made with beads containing 8% divinyl benzene and 2% styrene and other monovinyl monomers. So the cross-linkage affects the resin in two ways. As the number of cross-linkage increases, the dry wet capacity decreases. This decreased capacity results from the greater difficulty of substituting active groups on the copolymer, probably due to the steric factor. Okay, so the cross linkage affects the physical property also. Highly cross-linked resins is brittle. On the other hand, low cross-linked resins are highly swollen, therefore soft and easily deformed. The capacity. In the ion exchange operation, it is the counter ion which are put to use. The counter ion content of a given amount of material is equal to the fixed charges which must be balanced by the counter ions and thus is essentially constant. This amount this amounts to the fact that it is independent of particle size and shape and of the nature of the counter ion. So the total capacity of an ion exchange resin is the number of ionic, that is potentially ionic number of ionic sites per unit weight or volume of resin is known as capacity of the resin. The dry weight total capacity is usually expressed in milli equivalent per gram of anhydrous resin. Scientifically, it is usually expressed as milli equivalent per gram. The weight volume capacity is the number of sites per unit volume of water soluble resin. So, the net number of sites which are utilized in a given volume of resin in a given cycle is known as operating capacity. So, another term which is known as useful capacity, which is capacity when equilibrium is not attained, it depends on experimental conditions such as ion exchange rates, etc. There is another capacity which is known as breakthrough or dynamic capacity, which is utilized in column operation. It depends on operating conditions. There is also another capacity known as sorption capacity, which is the amount of solute taken up by sorption rather than ion exchange for specified amount of exchanger. The next one is the distribution ratio, so which is known as the ratio between the concentration of ion in the resin to concentration of same ion in the solution is known as distribution ratio. So the conventional unit, if you consider, so D will be equal to amount per kg of the dry resin divided by amount of that ion concentration, amount of that ion in liter of solution. So the amount, that means in milligram or moles or whatever may be the proper. It's proper since the units cancel during calculation. Then the distribution coefficient, which is concentration in 1 gram of resin per upon concentration in 1 milliliter of solution. So that is the distribution ratio or distribution coefficient. Then equivalency of exchange. Then resin selectivity. The strong cation exchangers like DOX50 is comparable in acid strength with hydrochloric acid and will form stable salt-like bonds with any cation. Similarly, strong anion exchanger like DOX1 is comparable to sodium hydroxide and will form a stable bond with many anions. Okay, the only ions which cannot be held strongly by one or the other of these resins are complex ions or organic ions, which due to their size or configuration are hindered from entering the interior of the resin particle. So that's why we have to select the resin. So with this statement, it does not mean that all bonds between the strong resin and the different ions are of equal strength. The ion exchange resin will have preference for the particular type of ions they will take to hold if given the choice. So it is this preference which is defined as the selectivity of the resin. In resin systems, the typical physical chemistry equilibrium constant is not strictly applicable. It is substituted by selective coefficient. So, for resin, for example, containing B ions placed in a solution of ion A and allowed to come to equilibrium, then the selectivity coefficient K AB. For monovalent exchange is given as follows. So K A B A to B. So concentration of A in resin into concentration of B in solution divided by concentration of B in resin and concentration of A in solution. So this can be written as like this: A plus Br, it is in resin, so that will be changed to that one AR plus B. So that will be equal to AR into B divided by A into Br. So where R subscript represents the resin phase. So types of functional groups which are present in the resin. So the functional groups may be the ammonium one, as already we have discussed, valence and nature of exchanging ions at low aqueous less than zero point 0.1 normal concentration and ordinary temperature. The extent of exchange increases with increasing valency. So sodium less. So sodium can be replaced by calcium, can be aluminum and thorium like this. This means that divalent anions are more tightly held by the resin and monovalent ions and trivalent ions than monovalent ions and trivalent ions more tightly than divalent ions. So this will exchange fast. So univalent ions exchange decreases with size of hydrated ions. The total solution ionic strength. Monovalent exchanges are usually little affected by the change in the total ionic strength. However, it becomes important if the exchanges are taking place in different valence, say mono-divalent exchange. Let us first consider monovalent exchange. Sodium chloride RSO3H monovalent, so H will replace, so we will get HCl and RSO3Na. So the exchange constant, that will be Na plus constant and H plus here. Na plus will be in resin, so Na plus constant H plus in it will be in solution, and here Na plus in solution and H plus in resin. So by substituting the values as follows: if X is the equivalent fraction of sodium ion in resin, that means Na plus in resin upon by C, the concentration, and Xna is the equivalent concentration of sodium in solution. So Na plus by Cr, and where C prime, sorry, Cr is the total capacity or normality of resin equivalent per liter, and C is the total normality of solution. So if you put these values, then this one will have the form like this. So this equation gives the equivalent fraction of Na plus in the resin as a function of solution with which the resin is in equilibrium. It may be noticed that the terms Cr and C do not figure in equation. This one C is not there, so concentration equivalent the total capacity of normal resin or normality has no role here. So similarly, monovalent with divalent ion, so representative will be there, so only square term will be there. So in this case, you will have the capacity or concentration will play the role, because this one term is square, so the C term will come here. So C CR is the total capacity of resin. So it is coming here. The normality of resin phase will depend upon the swollen volume of the resin. Okay. Then we'll move to the operating methods. Two types of operations are there: batch operation and column operation. The batch method consists of immersing the resin in the solution in a container and allowing the equilibrium to be established. The extent of exchange of ions is limited by the selectivity of the resin under equilibrium conditions. Therefore, unless the selectivity is quite favorable, only a relatively small part of the total capacity of the resin can be utilized. It is convenient to use a resin batch-wise, but it is generally impractical to regenerate the resin for reuse batch-wise. In the column operation, the ion exchange column with fraction collector. The column operation can be visualized as a large number of batch operators in series. The extent to which the exchange takes place in each one of these small batch operations is limited by the appropriate selectivity coefficient. The overall effect may be much more favorable. The successive batch operations in a simulated column may be considered to plates in a distillation column. So, in a majority of units, ion exchange containers are used and they are taken as vertical columns filled with the ion exchanger as shown in the figure. The resin is supported on a bed of graded gravel or some other filter base and the feed and regenerant solution pass through the column, downflow operation or off through the resin, that is off flow operation. The next one is the moving bed operation. Somewhat different type of column operation is that encountered in a moving bed or continuous counter current system. In such a system, the resin as well as the solution is made to flow through the system. A typical unit consists of two stages in which the resin is contracted counter currently with the existing stream and the regenerant stream. The advantage of moving bed operation are those with continuous operation, say constant supply of a product of uniform quality and reduced cost of space, capital and labor. There are some design problems due to the movement of resin. Maintaining a counter current flow of resin and solution depends upon the density of the two phases. And the ion exchange in mixed aqueous organic media. So the ion exchange that may not take place only in aqueous solution, but there must be the ions in both in the solution and in the solid. So ion must be free to move and the exchange takes place with water as a solvent and with solids which qualify. 1 minute. With water as a solvent and with solids which qualify as an ion exchanger, these conditions are usually met. Water, because of its high dielectric constant, is an excellent solvent for most inorganic and quite number of organic acids, bases, and salts. This is what justifies the choice of water as the phase for ion exchanges. Water, however, is by no means the only solvent which allows ion exchange to take place. There are other solvents with high dielectric constant in which electrolytes can dissolve and dissociate, and in which most of the ion exchanges are stable. They are ethylene glycol, methanol, ethanol, and acetone. So the last three solvents like methanol, ethanol, and acetone in particular have importance in ion exchange. They can be used with or without addition of water. So the addition of organic content reduces the dielectric constant of the solution, promoting thereby the ion pair formation between the ionic species and fixed ions of the ion exchanger. Consequently, with increasing organic content, the uptake of ionic species on the ion exchanger may increase. Sometimes the addition of organic content of the aqueous solution causes a decrease in the distribution coefficient of the ions. This is probably due to the attachment of ionic complex to the protonated organic solvent, making thereby the anionic complex less available for the solid ion exchanger. Now, if we consider specific ion exchangers, what are the specific ion exchangers we can use here? Dipicrylamine, picric acid, trinitrophenol is picric acid, so it is 2,4,6 trinitrophenol is picric acid. So one OH group it is substituted by NH and they are linked together. Two picric acids groups are joined. So this is dipicrylamine. So dipicrylamine is a non-specific precipitating agent for potassium ion. The resin is synthesized from polystyrene by nitration, reduction, then condensation with picryl chloride and again nitration. Many compounds which form chelates with metal ions have been incorporated into resin, while polycondensation with phenol and aldehydes. To cite the example, there is one with anthranilic acid. It is selective for zinc and other transition metal ions. Other compounds which have been used are orthoaminophenol, anthranilic acid, diacetic acid, and metaphenylene diglycine. There are chelating resins containing groupings similar to those of the more convenient chelating compounds like EDTA, ethylene diamine tetraacetic acid, but attached to a cross-linked matrix of gross insolubility. Okay, then synthetic inorganic exchangers, different types and their characteristics. The hydrous oxides of polyvalent metals, insoluble acidic salts of polyvalent metals, salts of heteropolyacids, insoluble ferrocianides, synthetic aluminosilicates, miscellaneous inorganic ion exchanges such as synthetic apatites and sulfides. So hydrous oxides of polyvalent metals like manganese, tin, cerium. These are most studied compounds. Zirconium, titanium also in this class. So mixed hydrous oxides of di and trivalent metals, tri and tetravalent have also been investigated. The hydrous oxides of quinquevalent and sexvalent metals generally show cation exchange properties and are stable towards most of the commonly used reagents. Similarly, insoluble acidic salts of polyvalent metals like aluminum, chromium, iron, titanium, zirconium. So they include the phosphates, arsenates, antimonies, vanadates, molybdates, tungstens, tellurates. So mostly trivalent metals are these are which are used. Then salts of heteropolyacids. It may be phosphorus, arsenic, silicon, or germanium, and boron. XHM, the acidic one, XY12O40. So X is phosphorus, arsenic, germanium, and Y different elements such as molybdenum, tungsten, and vanadium. Then ferrocianides, insoluble ferrocianides. Ferrocianides of various metals like silver, zinc, cadmium, copper, all these metals can be studied. So these can act as cation exchangers with a high affinity for heavy alkali metal ions, especially for cesium. The ion exchange mechanism of ferrocyanide is rather complicated and not yet clear. Then the synthetic aluminosilicates. These compounds represent a great family of inorganic ion exchanges, and depending upon their structure, they may be divided into three categories: amorphous, then two-dimensional layered aluminosilicates, and aluminosilicates with rigid three-dimensional structure, the zeolites. In between, I have to check. Okay. And the miscellaneous inorganic ion exchanges, it may be of calcium, strontium, barium, cadmium, and lead. X may be phosphorus, arsenic, vanadium, chromium, manganese, all these things. The stability, this the structure, physicochemical properties, thermal stability, and ion exchange property of these materials have also been reported. The ion exchange properties of a wide range of sulfides have been studied. The sulfides are selective towards cation forming insoluble sulfides. The metal of sulfide is displaced by the appropriate ion in solution. And special properties and application can be used in radiation and thermal stability. This should be in the radiation stability combined with separation capability yield a system which is known as isotope generator. A radionuclide generator is a system or device which makes the repeated recovery of short-lived isotope in a pure form from a relatively long-lived parent isotope. Then we'll move to the application is ion exchange chromatography. It is used the separation of metal ions and anions, separation of organics, separation of ionized from non-ionized substances, separation of actinides elements, miscellaneous application. So separation of metal ions and anions. Detail you can go through the manual which is provided to you, the reading manual. Then separation of organics, separation of ionized from non-ionized. Here you use solid network of resin beads, liquid inside the bead or resin liquid. So the and the liquid surrounding the beads is the interstitial liquid. So low molecular weight solutes diffuse freely in this case. Separation of actinides. So then miscellaneous applications. Okay, then some summary and some terminal questions. So we'll have a little break, then we'll start the next one, that is the size exclusion chromatography or gel permeation chromatography. Just 5 minutes break. Okay, so the size exclusion chromatography, which is otherwise known as gel permeation chromatography. So is in this method, the separation are achieved on the basis of molecular geometry or molecular dimensions. So the size exclusion or gel permission, gel filtration chromatography or gel permission chromatography. So it falls in this category where the separation occurs basing upon the molecular geometry and molecular dimension. However, if you probe into another criteria of classification based on equilibrium and rate process, the exclusion chromatography, the technique appears in the chromatographic process where liquid and solid are in equilibrium. Thus, very rightly, the size exclusion chromatography is one of the important form of liquid chromatographic technique. So these top points will cover here the basic principle, gels and their important properties, classification, synthesis and properties, variables defining the utility of gel, unique features of the technique and some application. So now come to the basic principle. Here also we are using cross-linked polymers. So the packagings for size exclusion chromatography generally consist of cross-linked polymers of dextrans, polyacrylamides, styrene or silica. They have an open network. On observing the solvent, swelling causes an opening in the structure. The degree of cross-linking will determine the size of the holes. So basing upon the degree of cross-linking, the size varies. So different molecular weight, for example, this is one technique which is used to separate the polymers of different molecular weight, the size exclusion chromatography. So the first the static phase, that is the absorbent. So the pore size depends upon degree of cross linking. So depending on the pore size, different molecular polymers, they will pass through the pore and can be easily separated from each other. So they have an open network on observing on the solvent. On observing the solvent, swelling causes an opening of the structure, then the degree of cross-linking will determine the size of the holes. In this network of uniform pores, the solute and solvent molecules can diffuse, while in the pores, molecules are effectively trapped and removed from the flow of the mobile phase. The average residence time of the solute molecules depends upon their effective size. The molecules which are significantly bigger than the average pore size are excluded. Okay, the molecules which are significantly bigger than the average pore size, they will be excluded. That means they will come first from the column. As a result of which, they suffer no retention and travel through the column at the rate of mobile phase. The molecules that are appreciably smaller than the pore size can penetrate throughout pore network and thus remain entrapped for the longest time. As a result of this, the molecules which are able to penetrate the gel will spend part of their time sheltered from the moving phase. Between these two extremes, an intermediate size molecules whose average penetration into the pores of packing depends upon their diameters. The fractionation within this group is directly related to the molecular size and to some extent the molecular shape. Thus, there is a basis of separating molecules of different size. So, as you can see from the figure here, various molecular sizes are let this is a sample. Then when they are passing, small size they are entrapped here, bigger they are coming out of this. So bigger smalls are entrapped depending upon the pore size, then they are excluded. This is the schematic of a chromatographic separation on size exclusion column. It is important to note that the size exclusions are different from other chromatographic procedures. I am afraid whether I will be signed out or not. Yes, it's okay. Going on. What happened yesterday? Here there are no physical or chemical interaction between the analyte and the stationary phase. As a matter of fact, efforts are made to avoid such interactions because they may cause impaired column efficiencies. At this point, it may be important to introduce the term the exclusion limit. The exclusion limit is the molecular weight of that molecule that will just permeate the gel and be retarded. This can range from 1000 to several millions depending upon the gel. It should be kept in mind that separation are based on molecular size and configuration rather than simply its molecular weight. But generally, there is a correlation with the molecular weight. Also, generally, the molecules smaller than the exclusion limit can be fractionated down to a limiting size. Because if you can remember, in study of polymer science, the polymer molecular weight, there are different types of polymer molecular weight like number average molecular weight, weight average molecular weight, viscosity average molecular weight, different types of molecular weights there. So in this case, in size exclusion chromatography or gel formation chromatography, we can find out the number average molecular weight. It is number average molecular weight is related to the size of the molecule or the polymer. And what is the different types of polymers samples will be there, it will be separated and we can find out the number average molecular weight and also how many such types of different types of molecule are there in which range we can find out also the degree of polymerization and the polydispersity index And did you know polydispersity index is the ratio between the weight average molecular weight and number average molecular weight. So once we get the number average molecular weight and polydispersity index, we can find out the weight average molecular weight of the polymer also. So that's the thing which has been written or which is indicated in this paragraph here. So to the entire picture of fractionation by size exclusion chromatography can be visualized in some semi-quantitative term. Let VR is the retention volume for a solute with a chromatography column, and let V naught is the interstitial volume, that is void volume, that is the volume within the column which is available to the mobile phase. VL is the volume of water within the gel particles available for accepting the solutes. On the lines of GLC, we can write the following equation that VR, the retention volume for the solute, that will equal V naught into K into VL. Sorry, V naught plus K into VL, where K is some distribution coefficient. If the solute is completely excluded from the interior of the gel, then K equal to 0, and in that case, VR will be equal to V naught. Such marker substances are available. Now, if the solute can freely enter the gel, there should be no preference of water inside or outside of the gel, and thus K equal to 1. In that case, VR will be equal to V naught plus VL. Taking the case of molecules which can penetrate the gel to some extent but not freely, K value falls between 0 to 1. So, if you plot the molecular weight and retention volumes, the curve will be like this. So relationship between the retention volume and molecular weight of the solute. The steep region between the arrows, so this one from here to here is the fractionation range. That means the molecular weight range from here to here. So in case where sieving is the only phenomenon responsible for fractionation, K value is greater than 1 would never be encountered. However, sometimes these values are often suggesting the occurrence of phenomena like adsorption, hydrogen bonding, and ion exchange between the gel and the solute. So this figure, it is a typical behavior of variation of the retention volume and the molecular weight of the solute. It is clear that the molecule of differing in size can be separated chromatographically in the sloping region of the curve from here to here. By varying the degree of cross-linking of the polymer, the curve shifts horizontally in this direction or this direction. There are materials available for which fractionate molecules in various molecular weight ranges can be done. For example, if you take Cepatex G50, the fractionation range of for peptides and globular protein in the molecular weight range 1500 to 30,000, while the range for G G150 it is 5,000 to 4 lakh. So different columns we can take for different molecular weight. And the gel and their important properties. What are the gels? So we know what is gel. Refers to a fairly soft elastic material containing water. In the scientific context, the term acquires a wider meaning. A gel consists of three-dimensional network. Okay, that means it will have the cross-linked structure polymer, and when it will be placed in a desired solvent, it will swell up and to form a gel-like structure. Gel means more solid will be there, less solvent will be there. So it will form a gel. If more solvent, less solute, then it is a solution. The reverse is gel. The structural material, often consisting of cross-linked polymer, gives more mechanical stability. The shape within the gel not occupied by structural material is filled with liquid. So liquid occupies the main part of the gel. Some gels are soft and deform easily, is being the common picture. others are rigid and even brittle. There are many natural substances capable of forming gel and include polysaccharides from fruits and roots, proteins from animal tissues, inorganic silicates and phosphates. If we look at the gel from the chromatographic point of view and also from general property, two different types of gels can be distinguished. In the macromolecular gel, the microstructure is strongly heterogeneous with regions where matrix material is aggregated and regions where there is very little gel matrix present. In gel structure, virtually free from gel matrix allows larger molecules to enter. The microreticular gels, on the other hand, they show properties that the gel matrix is relatively distributed throughout the gel. They fractionate relatively lower molecular mass ranges rather than macromolecular gels. So, what are the important properties of gels for chromatography? First one, the matrix of gel should be inert. Any interaction between the gel material and the solute may lead to irreversible binding of the solute. The interaction may lead to chemical alteration of labile substances. In biochemistry, there is a risk of denaturation of proteins and nucleic acids. So, therefore, to avoid all these things, the matrix of the gel it should be inert. If the rigid material is there, if the right material is there, gel filtration chromatography is one of the few separation methods which is capable of giving quantitative yields. Then second one, the gel must be chemically stable. So within a range of pH and temperature, it must be stable. The gel that are used in practice are stable over years and months. The leaching of material from bed should be very low. Then low content of ionic groups. A low content of ionic groups is required to avoid the ion exchange effect. Charged groups will give bad yields of charged solute and asymmetric elution curve. This is it is impossible to avoid the charged groups, but the commercial available gels are very low ionic groups. So care must be taken during preparation or during synthesis of the matrix or the gel, that means polymer. So there should be less ionic groups may be there. And availability of wide choice of gels. For the adoption of a method of different problems, a wide choice of gels with same general composition but different fractionation regions should be available. For microreticular gels, the fractionation range is mainly determined by swelling properties. Gels with low content of dry substance in the gel give access to larger molecular weight molecules than those with high content of dry substance. So with macromolecular gels, the content of the dry substance is no longer the only variable which determines the fractionation range of the gel. The structure of the gel is also important. Then availability of gel with different particle size. The same substance should have different particle size. The particle size distribution should be very carefully controlled. A column of small particle size will generally give good resolution. If the particle size is increased, then the regions for zone broadening there it will be amplified. With the large particles, the diffusion in and out of the particle takes longer time, so flow pattern in large particle is inferior. On the other hand, the resistance to flow in a bed of large particle is lower. Thus, a compromise with regards to the particle size should be reached, giving a maximum zone resolution under a desired flow condition. Okay, so generally the commercial available gels are in bead forms. The mechanical rigidity of the gel particles. The mechanical rigidity of the gel grains should be as high as possible. काली यही समय bond is gone. Okay, you are there, Deva. So the force may cause the bed to compact reversibly or irreversibly, thus increasing the flow through the bed. The micro reticular gels with small content of dry substance, a correspondingly high exclusion limit, tend to be mechanically weak. So these gels are called micro micro reticular gels. Then move the classification, synthesis, and properties. So we discussed the characteristics which are needed for a gel to be useful in chromatography work. Now we'll discuss how they are synthesized. The classification of different types of gels are given here. So dextran gels, there is Cepadex. Then dextran N-methylene bisacrylamide gels, that is Cefacryl. Then polyacrylamide gels like Biogel, agar and agarose gels, styrene divinyl benzene gels like Styragel. So besides the above classes, inorganic materials like silica gel and porous glass are also used. So let us study the different gels here. The first one, the dextran gels or the Cepadex. Dextran is a polysaccharide built of from glucose residue structure. Yes, it's given here. Structure of Cepadex. Can I decrease the size? Yes. So it is a polysaccharide built up from glucose residue. It is produced from the fermentation of sucrose. The microorganism that is used for fermentation is Liconostoc meson- mesenteroids or Liconostoc mesenteroid strain, that is NRRLB 512. The native dextran has high molecular mass and a wide mass distribution like 10 to 300 into 10 to the power 6 Dalton. The raw material is first purified, partly hydrolyzed, then finally fractionated by ethanol precipitation to give a product of suitable average mass and narrow mass distribution. The glucose residue are joined by alpha 1,6 glucosidic linkage. Alpha 1,6. You can see here if this is 1, 2, 3, 4, 5, 6. This carbon is the glycosidic linkage, so this is 1 and this carbon is 6. So 1 and 6 they are linkaged by this oxygen bond, so which is known as the glycosidic linkage. So alpha means if this OH group they will be in the same side of the chain, then it is alpha. This if this will be opposite, then it is beta, as in case of cellulose. But in case of starch, it is alpha. So alpha 1,6, there 1,4 here. It is in sorry, in starch it is 1,4, but here it is in 1,6 glycosidic linkage. The chain are to a certain extent are they are branched. The branches are joined to the main chain by 1,2, 1,3 or 1,4 glycosidic linkage. If we prepare dextran by Liconostoc mesenteroids strain B512, the branches are joined by 1,3 glycosidic linkage. And dextran dissolves in water, but when it is cross-linked to form the gel, the polysaccharide chains of the gel form a three-dimensional network, and the material thus becomes insoluble in water. So Cepatex is manufactured by a bead polymerization process. In this process, an alkaline solution of dextran is soluble molecular mass distribution is suspended in an organic solvent which is immiscible with water. Then stabilizers are added to stabilize the suspension. When the suspension is stirred to form an emulsion, epichlorohydrin reacts with dextran matrix forming glyceryl links between the chains. After the completion of the reaction, the product is washed thoroughly and allowed to shrink in water alcohol mixture and then dried. So Separex, it is available as a free flowing powder consisting of regular bead form pharmaceutical chemicals is generally manufactured this one. When this is suspended in water, the beads swell. Drying and swelling of Sepadex is a reversible process. So chemically it is very stable. The weakest point of attack in the structure are the glycoside linkage, which are hydrolyzed at low pH. So that is the weak point. So it will the glycoside linkage it will hydrolyze and it will break. So it is stable in alkaline solution. Its prolonged exposure to oxidizing agents may cause an increase in the carboxyl group content. The increase of carboxyl group in the structure impairs the chromatographic behavior of the gel. It may be noted that initially Cepadex contains a very small amount of carboxyl group. So this amount is so low that most of the charge effect observed are attributed to Ronan effect caused by the solution. Then the dextran N-N-methylene bisacrylamide gel, that is cefacryl acrylamide N-N-methylene bisacrylamide, it is UNNH, acrylic acid acrylamide, then N-N-methylene group is there. So cefacryl is a dextran gel manufactured by cross-linking allyl dextran with N-N-methylene bisacrylamide. There are cross-links not only in dextran but methylene bisacrylamide molecules also bind to each other. This part is the dextran part, then this is also dextran, but here the acrylamide. Hypothetical structure is given here. So the cross-linking reactions make the gel partly macromolecular and the gels can be produced with fractionation ranges extending up to high molecular masses. They are mechanically rigid and high, bear high pressure up to 1 megapascal without compressing the bed. These gels are intended mainly for use with aqueous eluents. Two types of Cefacryl gels are available. They are Cefacryl 200 superfine and Cefacryl S300 superfine. The fractionation ranges over the most common molecular masses of water-soluble proteins. Since in these gels the structure is macroreticular, the slope of the selectivity curve is less than the micromolecular Cepadex gel. Due to large amount of methylene bisacrylamide in the gel, the adsorption effects are most pronounced that with Cepadex. Then polyacrylamide gel, that is biogels. Cross-linked polyacrylamides form gels with water and are known as biogels. They are mainly used for biochemical work. Unlike the Cepadex gel, these are entirely synthetic and made by acrylamide. CH2 double bond CH2. It is synthesized by copolymerizing acrylamide with the cross-linking agent N-N-methylene bisacrylamide. The concentration of the monomer can be varied to give different swelling characteristics, that means different degree of cross-linking and chromatographic properties. That structure is given here. acrylamide, and NN dash methylene bisacrylamide copolymer. So biogels are available from BioRed laboratories. They are produced by bead polymerization and are available as powder. They have a marked tendency to stick together and form lumps like Cepadex. Biogel is zero gel. Biogel is zero gel. What is zero gel? No hydrogel, solvo, other organic organogel, zero gel. That means in dry structure also it will have gel-like structure. It is reversible. It can absorb water to form hydrogel, and when it can absorb water and also organic solvent, it is known as zero-gel. When the dry powder is immersed in water, it swells to form the gel. Biogel is quite inert, and the weakest point for chemical reaction are the amide groups, which are hydrolyzed at extremes of pH. On hydrolysis, the carboxyl group formed impart the ion exchange character. Biogels are available in 11 types with different swelling characteristics and different fractionation ranges. Okay, then the agar and agarose gel. Agar or agar, as it was called earlier, is obtained from various species of seaweeds. It is a mixture of linear polysaccharides comprising mainly of D-galactose and 3,6 anhydro L-galactose residues. Partial structure is given here. These gels are unique, combining fractionation ranges at very high molecular masses with very good mechanical stability. They are a good supplement. They are a good supplement to the dextran gels and polyacrylamide gels. The agar gels with the lowest fractionation ranges corresponds approximately in their fractionation properties to the dextran and polyacrylamide gels. With the highest fractionation ranges, these gels can fractionate in the range intermediate between molecules and particles. So agarose gel has some advantages as a chromatographic material. There is a considerable amount of charge groups in the material. Because of the presence of charge groups, it is recommended to work at high ionic strength to mitigate the problem due to ion exchange effects. Another problem arises from the fact that agar agar chains are not linked by covalent bond. It makes the agar gels chemically unstable. So this amounts to the fact that they are less stable to pH extremes than the gels described earlier. Then we'll go to styrene divinyl benzene gels, that is the styragel. It's a class of polystyrene gel for purely non-aqueous separation of methylene chloride, toluene, trichlorobenzene, tetrahydrofuran, and so on. It can be used with water, alcohol, and acetone. These macromolecular gels have fractionation range from 1600 to 40 million. Styragel is available in 11 different types. These are manufactured by Dox Chemical. Okay, the beads are supposed not to change their volume with the change of solvent. Then the variables defining the utility of gel. The most important of the different properties is the fractionation range. Sometimes it is given as the upper limit of fractionation or the exclusion limit. When exclusion limit or the fractionation range are given, it should be stated that for what type of substances these data are obtained. These numbers vary with one type of substance to the another. For a given group of compounds, say globular proteins, polysaccharides, etc., they are fairly constant. Another important variable for of significance is the stiffness of the selectivity curve in the linear portion of the fractional range. So for zero gels, the water regain is the common measure of swelling capacity of the gel. Here it may be important to tell more about zero gels and aerogels. Different gels react differently to the removal of liquid in them. The group of zero gels shrink on drying to a compact material containing only the gel matrix. The aerogels, on the other hand, do not shrink. Instead, the surrounding air penetrates into the gel. So, aerogels, when brought in contact with the liquid, they take up liquid and return to the gel state. But in aerogels also, the air can be substituted by the liquid. So, that is the difference between aerogel and aerogel. Getting back to water regain capacity, it is usually expressed as an amount of water in milliliter imbibed imbibed by 1 gram of dry aerosol on swelling. It does not include the interstitial liquid between the grains. What happened, Pankaj? And the unique features of the technique. This is simple technique of size exclusion chromatography rapidly become very popular and almost become indispensable for biochemistry and also for polymer chemistry. Before we discuss more of its important applications, it may be desirable to look into the reason for its first adoption as a frontline chromatographic technique. The size exclusion chromatography can fractionate substances of very high molecular masses. Using this technique, certain problems in biochemistry can be resolved in a simple way. Typical problems of this type are resulting of solutions of proteins and other high molecular mass substances and determination of molecular weight of macromolecules. The chromatography column usually need no regeneration. They can be used over and again for a long duration of time without alteration in their chromatographic properties, provided in microbial growth also can be avoided. So some applications, the in broad sense there is the analytical application, preparative application and miscellaneous application that can be categorized into three. Then in analytical application, we have analytical group separation and analytical fractionation, then measurement of protein binding and complex formation and determination of molecular mass. These four categories are there. So in group separation, the one of the very common uses of gel filtration chromatography is the removal of interference between the final determination. So it is particularly important to remove low molecular mass interference before the determination of macromolecular components in mixture. The determination of proteins in spinal fluid is a typical example. The low molecular weight interference interferences are removed from the spectrophotometric determination of protein. Similarly, in analytical fractionation, the most important application of analytical fractionation comes closer to the fingerprint end scale with substance overlapping to a large extent. Many biological fluids have been characterized. The most important among these are plasma. So, the illusion behavior of plasma proteins have been investigated. The measurement of protein binding and complex formation. Gel filtration chromatography has been useful in the study of complexes between protein and low molecular masses. The principle of this measurement is simple. If the reactants are irreversibly bound to each other, the reaction mixture is fed to a column and the complex is separated chromatographically. Then determinants of molecular mass, as already we have discussed in the molecular mass of the macromolecular polymer. It can be separated to different molecular weight range and the molecular distribution polydispersity index can be found out. How many number of polymer chains having a specific molecular weight are there, then we can find out the number average molecular weight of the polymer. So then we can go to the polydispersity index and you can find out the weight average molecular weight also. In the preparative application, the preparative group separation and preparative fractionation two are there. So preparative group separation, in a large number of biochemical preparations, desalting and exchange of buffers is an important step. Theoretically, there is no problem in achieving this separation, but in actual practice, some problems may be encountered. If distilled water is being used as an eluent, telling may be more pronounced than at higher ionic strength. Moreover, dilution is another problem. So, it is proposed to use volatile electrolytes like pyridinium acetate and ethylene diamine acetate. The technique is not only confined to desalting of macromolecules, but it has also been extended to desalting of virus also. Then in preparative fractionation, so it is used as a tool for separating the proteins, their degradation products and their complexes. Isolation of antibiotics to specific antigens is a subject of great interest. The separation of an antibody from the antigen can be performed by gel filtration chromatography. Fractionation of a nucleic acid and animal virus are also been attained on agar gels. So others are also there in miscellaneous application. The gel electrophoresis, which is generally preferred in a porous gel polymer matrix. This is another application. Poly- Nucleopolysaccharides and antibiotics, alpha amino acids, okay, they can be also fractionated by this process. And high performance analytical applications, small polystyrene or microporous silica particles of 5 to 10 millimeter diameter we can use as the column bed. So this is all about the size exclusion chromatography. Okay, then okay, thank you.
हेलो। सोमनाथ।
हेलो। हेलो।
हाँ
आर
सोमनाथ,
यू
आपने
देयर?
एग्जाम फॉर्म फिल किया है क्या?
एग्जाम फॉर्म जून में।
जून में आएंगे?
हाँ, अभी तक आया नहीं शायद। मार्च में आएगा। फरवरी के लास्ट वीक मार्च में। हेलो। हेलो।
हाँ सॉरी, कनेक्ट हो गया था। अभी एग्जाम फॉर्म वगैरह कब अपने फिल होंगे? पीजीडीसी के, डीएससी की?
अब मार्च में आएगा भाई।
मार्च में आता है?
आप हाँ, ये देखिए, मैं चैट बॉक्स में अपना फ़ोन नंबर दिया है, उसको आप सेव कर लीजिए, ठीक है? एक ग्रुप बनाएंगे व्हाट्सएप का, क्योंकि जितने भी स्टूडेंट है वो सब क्लास करेंगे। तो आप कहाँ से हैं?
नहीं, मैं तो इधर से गुड़गांव से हूँ, दिल्ली से, एनसीआर से।
अच्छा, तो आपका स्टडी सेंटर के दिल्ली 1 2 3 कहाँ का है?
मेरा ये 2 का है।
अच्छा। देखिए,
हाँ।
मेरा तो 3 का है, दिल्ली 3 का, ठीक है? लेकिन मेरा एक्चुअली
हाँ,
क्या है कि क्लास, आपने क्लास क्या अटेंड किया था क्या? कब एडमिशन लिया था आपने?
मैंने अभी अक्टूबर में एडमिशन लिया, 2024 में। ठीक
अच्छा,
है।
तो भी ठीक है। आप एक काम करिए, एग्ज़ाम फॉर्म आएगा मार्च में, ठीक है? आप धीरे-धीरे करिए, ठीक है?
मार्च में आएगा ना? और एग्जाम इसके कभी जून में होंगे कि दिसंबर तक होंगे? कुछ आइडिया है?
देखिए, आपने आपने मतलब 24 में दिए थे ना, तो एक काम कर सकते हैं। आप एग्ज़ाम दे पाएंगे कि नहीं, ये भी नहीं, आप 1 साल बाद ही दे पाएंगे, ऐसा तो मुझे पता है, ठीक है? तो आप एक काम करिए, जितने
हाँ।
भी पेपर आप दे सकते हो उसको भरिए, ठीक है?
हाँ।
अगर एक साथ 4 दे सकते हैं तो वो भी भर दीजिए।
बट एग्जाम फॉर्म भरने का ऑप्शन नहीं आ रहा, उसमें लिखा है दिसंबर 24 में क्लोज हो गया है, इसलिए मुझे लगा कि शायद आप लोगों को पता होगा।
दिसंबर 24 का हो गया, एग्ज़ाम भी हो गया, रिजल्ट भी आ गया, ठीक है?
हाँ हाँ।
अब
ओके।
जब आएगा तो जून 2025 को आएगा, वो मार्च के बाद आएगा, ठीक है?
तो हमारा जो एडमिशन है वो पीजी डीएससी जो डिप्लोमा है वो 1 ईयर में होता है ना, सेमेस्टर वाइज नहीं है ना, आई थिंक?
नहीं नहीं, सेमेस्टर नहीं, पूरा 1 ईयर का है। अब आप एग्ज़ाम
आपने
फॉर्म
एडमिशन
जब
कब लिया
आएगा,
था इसमें?
मेरा बहुत पहले का है, मतलब वो 2022 का है।
अच्छा, 2022 का है। तो जैसे मैंने अभी
हाँ
2024 में लिया है, अक्टूबर में लिया है।
जी।
ठीक है, तो मेरा एग्जाम फॉर्म मार्च में भर जाएगा, ऐसा ही है या दिसंबर में भरना पड़ता है?
मार्च में आएगा।
हाँ हाँ।
मार्च 2025, मतलब एक दो महीने बाद क्या आएगा, ठीक है? अब
तो
तो
उसमें
फरवरी मार्च
सारे
खत्म
सब्जेक्ट का
खत्म
आएगा?
होने वाला है। हाँ,
सारे सब्जेक्ट का आएगा कि किसी ऐसा चॉइस रहता है कि आपको कौन कौन से सब्जेक्ट का फिल करना है?
देखिए, आप एक साथ 4 भी दे सकते हैं, एक साथ एक भी दे सकते हैं, ये आपके ऊपर डिपेंड कर सकता है, ठीक है?
ठीक है, ओके।
जब एग्जाम फॉर्म का लिंक आएगा तो उसमें आप क्लिक करके देख लेना पूरा, ठीक है? लिंक अभी एक्टिवेट नहीं हुआ। अब मेरा फ़ोन नंबर है, इसको सेव कर लीजिए, व्हाट्सएप में एक हाई लिख दीजिए, ठीक है? और एक व्हाट्सएप ग्रुप भी बना लीजिएगा, जितने भी स्टूडेंट कल परसों तरसों आएगा वो सबको ऐड कर लीजिएगा, ठीक है? ओके। अब मैं फ़ोन रख रहा हूँ।
नंबर तो आया नहीं मैसेज में, चैट मैसेज में।
देखिए, ये चैट बॉक्स में देखिए।
नहीं आया है।
देखिए ना, देखिए, मैं आपका जो पंकज लोधी आपने फैकल्टी लोग के लिखे है, उसके बाद मेरा नीचे है।
इसमें तो
चेक
नहीं है
करिए।
कहीं।
ये इधर चेक करिए, इन कॉल मैसेजेस।
हाँ, मैं वही देख रहा हूँ, मेरा बस मैसेज, उसके बाद तो रिप्लाई किसी का आया ही नहीं है इसमें।
तो फिर आप रिप्लेस करिए।
हम्म,
हाँ, देखिए, हेलो सर बोल के बाद लिखा हुआ है, एकदम फ्लैग, इंडियन फ्लैग है उसमें, देखिए। हेलो।
हाँ हाँ, बट इसमें मैसेज नहीं आ रहा, डिस्प्ले नहीं हो रहा कुछ भी। चैट मैंने अभी हाय
देखिए।
लिखा है। हाय का आपको आया?
हाँ, देखिए, मैं अपना फ़ोन नंबर टाइप कर रहा हूँ, अब देखिए हाय तो आ गया, तो मेरा तो, आपका
हाँ,
तो दिख
आया
रहा है,
आया
मेरा दिख रहा
आया,
है।
ओके।
हाँ,
आएगा आएगा।
हाँ, ये नंबर सेव
आया।
कर लीजिए, और एक व्हाट्सएप ग्रुप में जितने भी स्टूडेंट आएंगे वो सबको ऐड कर लीजिएगा, ठीक है? तो
ठीक है,
24 का
ओके।
क्लास रहेगा, ठीक है? ओके।
हम्म, ठीक।
मैं फ़ोन रख रहा हूँ।